Welcome to MathStat341, lecture day around 25. And so today we're going to see applications of Stirling's formula. So if there was a pop quiz today, it would be, what is Stirling's formula? And Stirling, which we've seen a few times, is n factorial is approximately n to the n e to the minus n square root of 2 pi n. A little bit more accurately, n factorial is n to the n e to the minus n square root of 2 pi n, 1 plus an error of size 1 over n. And in fact, you can have an expansion going on and explicitly write down what is the 1 over n term. The next term is of size 1 over n squared and 1 over n cubed. If you think about it, it seems like, well, if n is large, like, a million, then this term is 1/1,000,000th the size of the main term. But the main term is so huge that the error itself is large. Okay? So it will be smaller than the main term, but it will still be significant. And so what we want to do is we want to give a couple of proofs of either Stirling's formula being true or at least Stirling's formula being reasonable. One of my favorite proofs of Stirling's formula is a backdoor approach using the central limit theorem. And it's really nice when you can do something like this, when you can actually get Stirling as a consequence of the central limit theorem. So it's going to be the central limit theorem applied to something nice. And it's going to be to a Poisson mean variable. So you should have read about these by now, but I don't think we've covered it yet in class. So we'll say x is Poisson with parameter lambda if the probability that x equals n is lambda to the n e to the minus lambda over n factorial. And this is, of course, for n greater than or equal to 0, else it's 0. So what's the first thing you need to check? So I've given you my claim. What should you check?
We check if it actually is.
Yeah. Is it a probability distribution? So non-negative is easy. And then the sum, n goes from 0 to infinity of lambda to the n, e to the minus lambda over n factorial. And this is just e to the minus lambda, the sum, n goes from 0 to infinity of lambda to the n over n factorial, which is the definition of e to the lambda. So you get e to the minus lambda, e to the lambda, which is 1. So it is a probability distribution. Have we proven in class, I think we did, that e to the a, e to the b is e to the a plus b using the binomial theorem? Did we prove that? Ah, crap. All right. Yeah.
Don't we know that just from like multiplying exponentials?
No, we do not.
No.
And so if we haven't done it, then we actually have to spend time on this. So e to the a, e to the b is e to the a plus. Well, we don't have to, but I won't be able to hold my head up high. You don't. So we actually have to prove this. Now, what you were remarking is exactly right. Of course it's true, right? Laws of exponents. No. What does e to the a mean? E to the a means the sum, n goes from 0 to infinity, of a to the n over n factorial. E to the b is the sum, say, m goes from 0 to infinity, of b to the m over m factorial. And you have to show that this double sum is the same as the sum of a plus b to the k over k factorial. I'm going to do the math fast and loose. So this is the same as the sum, k goes from 0 to infinity, the sum L goes from 0 to k, a to the L, b to the k minus L, over L factorial, k minus L. And what I'm doing is saying, look, when I multiply the two terms, I'm going to get a to some power and b to some power. Let's collect all the terms where the sum of n plus m is equal to k. So k will be n plus m. And how many terms have a value of k? Well, I could have a to the k, I could have a to the k minus 1, I could have a to the k minus 2, all the way down to a to the 0. And that's why L goes from 0 to k. It's how many powers of A do I have, so that the powers of A plus the powers of B is equal to K. A comes in with its n factorial, that becomes an L factorial. The B is going to come in with a K minus L factorial. Now, if you look at this, actually no, you don't even need to look at it. You should be listening to this. What is it screaming at you that it needs? Algebraically. What is it missing? Any thoughts?
So like we really want a K factorial
Yeah.
on top, because then it's binomial.
Because then you have a binomial coefficient. So we'll put a 1 over K factorial over here so it's legal. You can't just multiply by K factorial, but you can if you divide by it. And since the sum is only over L, this is the same as the sum. K goes from 0 to infinity. 1 over K factorial, looking good. Sum L goes from 0 to infinity. K choose L. A to the L, B to the K minus L. Oh, well that's just A plus B to the K. And so now you get the sum, K goes from 0 to infinity, of A plus B to the K over K factorial, which is e to the A plus B. And so this is actually a good definition or good notation. It's good notation. What is the inverse of cosine? My body's rebelling at this. It's so painful. What is the inverse of cosine? 1 over cosine is? Secant. And what's 1 over sine?
Cosine.
So we can't choose to have the derivative of the product of the derivatives, the derivative of the quotient of the derivatives. The universe is structured how it is. We have no choice in the matter. But come on. We could associate cosine and cosecant and sine and secant, but we chose not to. So you want to think about, are you using good notation? When you see e to the a, you should be thinking this. There's a wonderful generalization of this when A and B are matrices, because in general matrices don't commute and the formula becomes very interesting. So one of the great things about Poisson random variables is if you have two Poisson random variables and you add them, you get a Poisson random variable. And so we'll prove this later when we get to generating functions, or maybe we'll quickly do it right now. So if xi is Poisson lambda I, then let's do lambda I. Lambda 1 plus x lambda 2 is Poisson with parameter lambda 1 plus lambda 2. So this would be a nice way to review how we do probabilities. So the density function is going to be, and I'll use an integer n because it's going to be a convolution, but it's not going to be over discrete things. It's going to be a sum over all n. The density for the first one at, say, m, and the density for the second one at n minus m. Right? That's how we're going to get the first plus the second to equal n. Well, because it's a Poisson, I want to have a non-negative integer argument. So what are the possible values of m looking at this? So what values will m take on? So m is in yes?
Positive integer.
Almost.
Including 0.
Including 0. So they'll allow 0 to hang. What about over here, n minus m? Then that would tell you m is in, if m is as large as n, we're okay. If m is greater than n, we're in trouble.
It's less than or equal to n.
So n can go from 0 to n. So this should be a sum, m goes from 0 to n. So now we put in what the values are. So it's going to be a sum, m goes from 0 to n. The first one is going to be e to the lambda 1, and then we'll have looking at a definition, it's lambda 1 to the m over m factorial, and then we'll have e to the lambda 2 to the n minus m over n minus m factorial. And this is almost the same calculation we did a moment ago. We have lambda 1 to the m, lambda 2 to the n minus m factorial, n minus m factorial. I want to multiply this by n factorial over n factorial. And I will get e to the lambda, oh, so these should have negative signs. E to the negative lambda 1 plus lambda 2, lambda 1 plus lambda 2 to the n over n factorial. So when the dust settles, you get that the sum of two Poissons is Poisson. So it's another stable distribution. The shape doesn't change. The parameter lambda changes. What happens is we keep taking more and more and more Poissons. What should it converge to? Why 1? So we keep adding independent copies of, say, Poisson. So we have, xi is, say, Poisson with parameter 1. x1 plus xn should be a Poisson with what parameter?
Parameter n.
With parameter n. But what should this also be converging to? We know it's exactly equal to a Poisson with parameter n. But what should it be getting close to if we have a sum of independent copies?
The normal?
It should be getting closer and closer to a normal. It's not going to be the standard normal because the mean is not going to be 0. But it should be converging to a normal. And so the idea is we can actually use this to deduce things about n factorial. Because the probability, you can see, has an n factorial in it. So we know the probability that x1 plus xn equals n, that's equal to e to the minus n, and then the parameter is just n, so we get n to the n divided by n factorial. For a lecture that's supposed to be on Stirling's formula, evaluating the probability here is quite a good thing to see, right? We've got an e to the minus n and an n to the n divided by n factorial. Dear Lord, we're only off by a square root of 2 pi, or 2 pi n. Huh. Do we know anything that has a square root of 2 pi or a square root of 2 pi n? So it's in Stirling, but where else have we seen a square root of 2 pi or... The normal's normalization constant, right? Everything is setting up for us to actually get Stirling's formula from the central limit theorem. If we know that this converges to a normal. So the first thing we need to do is we need to compute the mean and the variance of the Poisson random variable. So we have the expected value of x if, say, x is Poisson with parameter lambda. All right, so what we would need to do is we would need to calculate the sum, and it goes from 0 to infinity, of lambda to the n, e to the minus lambda, over n factorial times n. The probability we get n. We could do this with differentiating identities. We could do e to the lambda equals the sum and goes from 0 to infinity of lambda to the n over n factorial. And then what would we apply to both sides? Yes?
You would differentiate?
So we would differentiate by what?
By lambda.
So we could do d by d lambda, but I want to have a lambda to the nth power. So after I differentiate by lambda, what should I multiply by? Lambda. And so we start off with our identity. We apply the operator lambda d by d lambda. And okay, what's the root of e to the lambda? What's the derivative of e to the lambda?
Oh, wait.
Right.
E to the
It's just e to the lambda. So we just get lambda e to the lambda is the sum and goes from 0 to infinity of n lambda to the n over n factorial. So lambda is the sum and goes from 0 to infinity of n e to the minus lambda lambda to the n over n factorial. There's the mean. So if you have a Poisson random variable with parameter lambda, its mean is just lambda. Good mean. Okay. You could have also said, well, you know, I've got this sum. Well, when n equals 0, there's no contribution. This is the same as the sum. N goes from 1 to infinity. Lambda to the n e to the minus lambda over n minus 1 factorial. I've got an n minus 1 factorial down below. How should I write lambda to the n? I've got an n minus 1 factorial. How should I write lambda to the n? It's all about algebra.
N minus 1 plus 1.
Yes, n minus 1 plus 1. This is the same as lambda to the n minus 1 lambda. So that means we just pull out a lambda and we get something that sums to 1. We've just shifted our index. We have n going from 1 to infinity, but we have n minus 1 everywhere. And so that's another way to do the calculation. We could also calculate the variance. We would need to calculate the second moment. So we've got a couple of ways to do the second moment, right? We could either calculate n squared. And so it's worth spending a little bit of time trying to figure out what is the easiest way to do things. And sometimes the easiest way might not be your first thought. So over here, we know the expected value of x is lambda. Instead of applying lambda d by d lambda, I mean, we could do that, and then we could apply lambda d by d lambda again, and we could use the product rule to handle the lambda e to the lambda term. We could apply instead d by d lambda. And if we apply d by d lambda, we would then get e to the lambda is the sum and goes from 0 to infinity of n lambda to the n minus 1 over n factorial. Apply again. And we would get e to the lambda is the sum and goes from 0 to infinity of n minus 1 lambda to the n minus 2 over n factorial. Right? This is the same as 1 is the sum and goes from 0 to infinity of n squared e to the minus lambda to the n. Okay, we have an n minus 2. I'm going to bring the lambda to the minus 2 over to this side as a lambda squared. I'm going to bring the e to the lambda over to the other side. And we'll have an n squared e to the minus lambda to the n over n factorial minus a sum and goes from 0 to infinity of just now it's going to be n e to the minus lambda to the n over n factorial. The reason I'm doing it this way is I already know what this answer is. What is this answer?
This one's lambda.
That's the mean. So this is just, as you said, that's just lambda. This is lambda squared. And this is the expected value of x squared. So sometimes it's actually easier to calculate not the second moment directly, but something related to the second moment. It just makes the differentiation cleaner. So now we get that the second moment, is just going to be lambda squared plus lambda. Therefore, the variance we subtract off the square of the mean, is just lambda. So the variance is lambda. When we come over here to think about what's going on, we were comparing this to a normal distribution. So it has mean n, variance n. So the Gaussian will have a 1 over square root of 2 pi sigma squared, or 2 pi n. That's precisely the square root of 2 pi n that's coming in Stirling's formula. Okay? So we have two ways to go from this point. We can start to do, oops, the email that was sent. So we have two ways to go. We could try to prove how Stirling follows from the central limit theorem, or we could try to just analyze Stirling's formula directly. Any thought as to which algebra we do first? Direct. All right. So the direct, there's two ways. There's one way that's really good and gives the right answer, and there's another way that's even better but doesn't give the right answer. It gives a weaker result, but it highlights a great mathematical concept. And again, we're running out of board space, so this has to go. You know, the idea is to learn methods, techniques, tools that will help you as you go forward. So the first is the integral test. How many remember the integral test from calculus? All right, there's a little split today. The integral test is something you should have seen. It's one of the powers of calculus. It allows us to determine if certain sequences or series converge or don't. This is the real This is the real difference between 150 and 151. In 151, we assume you've done sequences and series. You have a lot of different tests. You have the ratio test, the root test, the comparison test, the integral test. A lot of these tests are actually just consequences of the comparison test applied to the geometric series. The comparison test is almost like art. If I give you a quadratic and I ask you to stare at it and factor it, you know, sometimes you can just look at it and see. For the comparison test, this is being artistic. You have to look and say, I'm going to compare you to the following. And that's where you need some kind of inspiration. The root test, plug into, plug into, plug into, plug into. You know what to do. Quadratic formula, plug into, plug into, plug into, plug into. Right? It's mechanical. Which is a better method? Well, if you can just look at the right thing and compare, that's frequently faster. Just like if you can look at the quadratic, I see how to factor you. If not, it's nice to have something that's mechanical. So let's look at, we want to look at n factorial. But we really don't want to look at n factorial because this is a huge product. What should we look at instead? There is a product before you. Yes?
Take the log.
You take the log. So if we take the log, we have the log of n factorial. This is a Pavlovian response. Whenever we see a product, we take a log, and we convert this to a sum. So this is now a sum. Let's say n goes from 1 to n of the log of n. So it's the log of 1 plus the log of 2 plus the log of 3. So this, here's 0, here's 1, here's 2, here's n. It's going to be a slowly increasing function like this. And what we can do is, because the function is monotonic, it's never decreasing, it's only going up. We can get upper and lower bounds very easily by doing something like this. And here's 3. And so if you do it this way, you get a lower bound. If you do it this way, you get an upper bound. And so basically, this sum is approximately equal to the integral from 1 to n of the log of t dt. And if you want to calculate exactly what is the error, all you have to do is look at basically the last point on the left and the last point on the right. You know, on this one, we start off too small, but if we shift everything over, we've only missed by that extra box in the end. And you can actually even quantify it. It should be essentially half of the last box is a log of n, so it should be basically off by like a square root of n. Because 1/2 log n becomes log of square root of n. Anybody know the antiderivative of log t?
I remember that we might want to use integration by parts.
So you could try guessing, t log t. And if you take the derivative, when you take the derivative, it's a product rule, you get log t, which is good. Oh, but crap, then I get t times 1 over t. So I get log t plus 1. Oh, that's not so bad.
Oh.
I just need something that has a derivative of -1. What has a derivative of -1?
Negative t.
Negative t. And so when you put in things at 1, it doesn't really matter. When you put things in at n, you basically get n log n minus n. This is basically n factorial. And so, I'm sorry, the log of n factorial. And so you get n factorial is basically when you exponentiate, e to the n log n becomes n to the n e to the minus n. And as I said, the amount you're off by, well, if you do upper or lower sums, you have this extra log n, which when you exponentiate becomes an extra factor of n. You really want about half of that. That's where the square root of n comes from. So this is the integral test to give you a rough sense of what Stirling's formula should be. And we can see that this is the lower bound. The upper bound would be n to the n e to the minus n times n. And not surprisingly, the true result lies essentially between the geometric mean. There's a better way to look at this problem, which gives a worse result in this case, but it's a nice way of looking at problems. And the first is this method of dyadic decomposition. So let's consider the product, n factorial is 1 times 2 times n. Can somebody give me an upper bound for n factorial? Really easy upper bound that you know is true. N to the n, excellent. And the lower bound that you know is true. 1 to the n. Okay? These bounds suck. But that's how you start. Now let's make it a little bit better. What you did is say, look, I'm going to take the largest value every time. I'm going to take the smallest value every time. Let's split the interval in half now. So you go from 1 to to n halves, and then n halves plus 1, to n. For all of these, what's the lower bound?
N halves plus 1.
Yes, let's just call it n halves to the n over 2. And over here you would have 1 to the n over 2. And what would the upper bound be? And this would just be n to the n halves. And over here would be n halves to the n halves. So we would get n factorial is less than or equal to n halves to the n halves, n to the n halves. Well, this is the same as n to the n. And then we have 1 half to the n halves. So this is the same as square root of 2 to the negative n. Because the square root of 1 half is 1 over root 2. That's the same as root 2 to the negative n. We're supposed to have n to the n e to the minus n. We have n to the n root 2 to the minus n. That's not bad. With a little bit of more work, we can get better. I think if we try the next level, we get, instead of root 2 is about 1.4. If you do the next one, for the next is 1.807. So it's getting better. There's another way you could do this. Have we done the drowning swimmer problem in this class? This is one of my favorite problems in calculus. It's a great problem, and you should never, ever, ever do this in the real world. So imagine you're a lifeguard, and a swimmer is in the water, and they're drowning, and there's fortunately no one else on the beach.
You've done it.
We have done this, right?
Yeah.
And we did Aquaman.
Oh.
No, we just did the drawings from it, where you don't run straight to the, okay. Okay. Oh, no, I'm sorry, no, this is not the drawings from, sorry, this is the Farmer Brown problem, the one with rectangular fences, I'm sorry. Have we done rectangular fences? So, if you have a fixed amount of fence, you want to maximize the area. How do you maximize the area? Subject to, say, x plus y is the semi-perimeter S. Well, you could look at the function area of x is going to be just x times s minus x, or sx minus x squared. It's not going to be maximized at the endpoints because that's going to have area 0. You take the derivative, you get a prime of x is s minus 2x. So the critical point is x is s over 2, so you get a square. So if I have two numbers with a fixed sum, the largest product is when they're the same. You could also, of course, plot this, and if you plot this, you know, here's 0, here's s over 2, and you see it's a quadratic, and the, I'm sorry, this is s, and then s over 2 is right here. So we can actually use this for Stirling's formula. If we look, you know, 1 and halves, dot to n, well, when I look at all of these numbers, the product is less than if I take the middle twice. So this would be 3n over 4, right? I have to square it, so I take it twice, and the number of pairs I have is no longer n over 2, it's now n over 4 pairs. And in the other one, it would be n fourths squared to the n fourths. All right, so I get an n to the n halves, n to the n halves. Good. That's still going to be an n to the n. Now I have 1/4. I have to take the square root of that. So it's going to just be 2. I have a square root of that, that's going to be another 2. Then I've got the square root of 3, but that comes down below. So I get 4 over square roots of 3, I believe, to the minus n. And so you can do stuff like this to get pretty good estimates for Stirling's formula. A really nice question is, if you keep doing this process, this dyadic decomposition, will it converge? Is there a way to make the algebra work out and converge to getting n to the n e to the minus n? You know, forget about trying to get the square root of 2 pi n. Can I see that these numbers are going to converge to e? But this idea of being able to do quick upper and lower bounds is extremely valuable. I'll do one more example. Oh, I want to keep this on the board. So I'll erase this part over here. So there's a sum you should all have seen. 1 plus 2 plus 3 all the way up to plus n. So what's the sum of the first n integers?
n times n plus 1 over 2.
Good. N times n plus 1 over 2. One of the ways to see this is just write the numbers backwards. And if you write them backwards, each sum is n, and I have n plus 1 sums. So if I sum it like this, I would get, you know, twice my sum is n plus 1 times n. Therefore, the sum is n plus 1 over 2. When I look at a sum like this, I want to just get a quick sense of what is its order of magnitude. So clearly it's less than n squared, and clearly it's greater than 1. Right? Well, I could actually replace the 1 with just n, take the smallest term every single time. The problem is these two bounds are not the same order of magnitude. And so because they're not the same order of magnitude, I don't understand the true size of this. For a lot of applications in computer science or statistics, you want to know how long is something going to take to run. And a lot of times this will give you the runtime. So we want a better order of magnitude. Well, if we do this dyadic decomposition, this would be less than equal to, if I look at the first n over 2 numbers, I would have n over 2, n over 2 times, and then for the last n over 2 numbers, I would have n. And that would be a better upper bound. And for the lower bound, from 1 to n halves, I take 1, so I would have 1. And then for the next n half numbers, I would take n halves. And so I get n squared over 4 is less than or equal to, so here we're going to have n squared over 2, n squared over 4, so this would be 3/4 n squared. So the true answer is really about a half n squared. We've got it's between n squared over 4 and 3n squared over 4. That's not bad. You know, we don't have the right constant factor, but we at least have the right order of magnitude. So again, as you go further and further in math and statistics, you're going to get more involved equations, more involved relationships. It's going to be very hard to look at them and see what's going on. If you can do any quick calculations to get a sense of, well, how bad is this term? Is this something I'm going to need to worry about? That's wonderful. And so this idea of dyadic decompositions, so we keep splitting things up, and then on each one we get a bound, and then we split each one of those up again and we get a bound, and we feed them all together. So what would you love to be true about n? What kind of number would you want n to be? More than just even. Even is a stop. Power of 2. So for a lot of these calculations, you can see it's screaming at you, please choose a power of 2. For a lot of algorithms, they run a lot more efficiently if you take a power of 2, just because of how you divide things up. And so here, technically, if this was a post-core class, I would have to worry about a little bit of error analysis, and what if n is not a power of 2? This is the advantage of doing this as a pre-core 300 level class, and you say, beauty. Okay? And just leave it like that. Okay? Because no, when you put in all the details, it often kills the result. And you get so caught up in doing all the algebra to make it rigorous that the beauty of the idea is gone. Here, we can get quick results without doing too much trouble. All right, so we have on the order of 10 minutes left, and the goal is to prove the claim from Stirling's formula, assuming the central limit there. And then, of course, this means later in the semester, what should we do?
Prove the central limit.
Yes. Now, what is the limit as x goes to 0 of sine of x over x? Have we calculated this before? In this class? Okay, so what's that limit? How would you calculate this limit? We've got 0 over 0.
Use L'Hopital.
You use L'Hopital. So it's the limit as x goes to, you know you've made it when your name becomes a verb. L'Hopital, right? Or command. Derivative of sine is? Okay, and so what will that limit be? C1. This is illegal mathematics. In using L'Hopital's rule, you needed to know the derivative of sine is cosine. How do you prove the derivative of sine is cosine? You need to use this limit. You can't use L'Hopital's rule unless you can independently prove for this problem that the limit of sine of x over x is 1. Well, then why the hell am I using L'Hopital's rule? Because I've already, it's a consistency check of L'Hopital. But you've got to be very careful in mathematics that if you put something off to the side, that when you prove it, you don't use any consequence of it in the proof. So when we prove the central limit theorem, we can't use anything about Poisson random variables. Okay, not a big deal. Yeah. Again, it's not a problem in this case. I just want you to be aware of this difficulty, that a lot of times people accidentally assume what they are trying to prove. I have gotten a tremendous number of proofs of Fermat's last theorem that assume Fermat's last theorem, and remarkably show Fermat's last theorem follows. Actually, sadly, not all of them can do that, but that's another story. So, CLT implies Stirling. All right, we're off to the races. So x is Poisson with parameter n that implies it has mean n and variance n. So I claim, and this should all be in the book, the probability that x minus n is less equal to 1/2, yeah, is basically the integral from n minus 1/2 to n plus 1/2 of 1 over square root of 2 pi n e to the negative x minus mean squared over 2 standard deviation dx. And what I'm doing here, here's n plus 1/2, here's n minus 1/2. I've got to be careful because the Poisson is discrete. So the Poisson takes on the values 1, 2, 3, 4, sorry, 0, 1, 2, 3, 4. And so if I want to talk about the value of the Poisson being n, if I want to compare that to the standard normal or shifted normal, I've got to be careful. I should really say it's equal to the probability from n minus 1/2 to n plus 1/2. Those are all the values that we're going to consider corresponding to n. Very similar to what we did in the baseball stuff. All right. So when you look at this integral, x, we can write x as maybe n plus t. T goes from minus 1/2 to 1/2. So this integral is basically 1 over square root of 2 pi n. I can take that out. Integral t goes from minus 1/2 to 1/2. E to the t minus n. Okay, that's just e to the minus t squared over 2n dt. And n is really large. What can you tell me about this integrand? How would you approximate that integral? Approximately, what is e to the minus t squared over 2n?
Well, 2n is really large, and it's approximately like.
So n is very, very large.
Then that would be e to the 0.
Right,
So it'd just be 1.
right. Think of n as my hatred for the Yankees, okay? So what would t squared, doesn't matter what t is. I'm dividing it by Miller's hatred of the Yankees. That's an exponent of 0. E to the 0 is 1. I'm integrating over something of range 1. So this integrand is essentially 1. It doesn't change by that much. If you wanted to, I could actually expand this and integrate it term by term. Ooh, if I do that, I'll get a 1. Then I'll get a minus t squared over 2n. There's my correction term of size 1 over n. And then the next one would be size 1 over n squared. And you can see the series expansion coming. So this is approximately 1 over square root of 2 pi n. But we've already said that this should be, the probability is e to the minus n, n to the n, over n factorial. Right? So all we have to do now is just cross multiply, and we get n factorial is about n to the n, I'm just writing them in a different order, e to the minus n, square root of 2 pi n. I am trying to convince you to love mathematics. You know, we did Newton's method a few days ago, and doubling the digits of accuracy every iteration. Yes?
Oh, and yeah, this is all assuming that n is large.
This is assuming n is large. And Stirling's formula only works when n is large. So when n is tremendous, this should be a really good approximation for n factorial. And if we wanted a better job, we would just go to this integrand, and we would write this as 1 minus t squared over 2n plus t to the 4th over 2, 4, I think it would be 8n squared minus dot dot dot. And then as you integrate the pieces term by term by term, the next one, I'm going to integrate t squared. I'll get t cubed over 3, right? So I integrate all this from minus 1/2 to 1/2.
Because that's the expansion of e.
Yeah, e to the minus t squared over 2n. So if I integrate it term by term, the first piece is going to give me 1. The next piece is going to get t cubed over 3. So 3 times 2 is 6. but I've got a t cubed, so it's going to be a 1/8, but I double it because I have the other one, so it becomes 1/4. So I think you get minus
124.
So see, I had a 6n down below, and then I had to double it. I had a 2. I had a 1/8. So I think it's 1/24n. So something like that I think should be the next term. I think the next one was actually 1/12, so I feel like I'm off by a factor of 2 somewhere. But I'm not too concerned. This is just trying to give a quick heuristic of what's going on. But you can see the new terms coming in. And you're also getting factors like square root of 2 pi. And so the big question is always, how is everything connected and related? There are certain numbers that just keep appearing. And I'm not sure if Stirling at Yale was the first one to remark this, but he's definitely one of many to remark. If the Greeks had been really intelligent, they would have constructed not pi, but 2 pi as their constant. And the question is, which constant appears more often, pi or 2 pi? How many of you have done physics, electricity, magnetism? You might remember the 1/4 pi epsilon naught. Yes? In terms of the force of electricity, the 2 charges. The 4 pi is due to the surface area of the sphere. You often find is like, I think 4 pi epsilon naught. Is it 4 pi epsilon naught or k naught? It's been so long. I think it's epsilon naught. And so there the question of what should you use? Actually 4 pi, the surface area of the sphere, has its proponents. We have Pi Day celebrations every year. When do you have Pi Day celebrations? March 14th. And at what time? Nope.
Oh, the next.
Yeah, 1:59. And how many seconds? 26. So you could actually still do it. At 1:59 and 26 seconds, that's when you should celebrate Pi Day. It's unclear if it's supposed to be AM or PM. Most schools seem to celebrate it at the PM time. There are proponents of Tau Day. Tau is twice pi. So if pi is 3.14, tau is 628. Which is, you can actually still celebrate that, but it doesn't fall during the academic year, so it makes it harder to have tau have proponents. But you really want to think, whenever you see these constants, why is there a pi coming in when I'm looking at factorials? When I'm normalizing the normal, the Gaussian, why am I getting a square root of pi, or square root of 2 pi? Where are they all coming from? Well, we see that the moments of the normal are connected to the special values of the gamma function. The gamma function is the generalization of the factorial. They're all connected. And this gives you this wonderful number that -1/2 factorial, number of ways to arrange -1/2 of a person with order counting, is the square root of pi. So, a lot of great stuff again today. Yes?
Can we go over the rounds again? N minus 1/2.
Sure, because when we're looking at what's going on, we have a discrete random variable. It takes on values at n minus 1, n, and n plus 1.
Right.
But it's converging to a Gaussian, and the Gaussian is continuous.
Oh, okay.
So how should I assign the probability for something like n? The best I can think of is, well, let's just take all the things that are closest to n, and that probability goes to n. That's why we have n minus a half. Oh, and this should be n plus 1/2 up here.
Right.
Yes, otherwise the integrand would be 0. But so this is remarkable that we can actually get something like Stirling from the central limit there. And this gives you another key perspective about being a mathematician, being lazy. When you have a result, what can you extract from it? What other things can you get from it? We saw differentiating identities again today, where when we had an identity, we could generate new identities from it. I feel like one of these TV shows where the first 100 math majors, stats majors get a pair of Ginsu knives. But you get all these new identities from one. And that's the power of differentiating identities. All right, so this is a good place to stop. If you